Chelsea Finn from Stanford as our next speaker. She is an assistant professor in computer science and electrical engineering, where she had the IRIS lab studying intelligence through robotic interaction and skill. She just very recently received her PhD roughly 2 years ago. She has been awarded the ACM Doctoral Dissertation Award and various other awards, like being MIT Tech Review Under 35 Pioneer. And so we're very excited to have her talk about MetaLearning symmetries.
Great, thank you for the introduction. And feel free to ask questions throughout or at the end, especially if anything isn't clear. So my work is kind of at the intersection of machine learning and robotics, and a lot of the motivation for both the machine learning work that we do as well as some of the robot learning work that we do is really along the lines of enabling robots to develop broadly intelligent behavior in the real world through learning and interaction. And that involves some of the robots shown here, trying to allow robots to use tools to lift objects, manipulate children's toys, or figure out how to perform a task by watching a person do a task. And one of the reasons why we like to study robots is that I think that they embody many of the real challenges of intelligence that humans are faced with when trying to learn how to make sense of the world. And one crucial bit about robots is that for robots to actually be useful, you don't just want a robot to do one very narrow thing. If you want to actually deploy a robot into human environments, you want them to be general purpose, such that they generalize across tasks, across objects, and across environments. And I think that this goal challenges a lot of the core aspects of our machine learning algorithms today. And this also motivates a lot of for us, a lot of the work that we've done on the topic of symmetries and data augmentation. In particular, I think that we often find ourselves in a situation that looks like this, where our train distribution is a lot more narrow than the desired test distribution that we'd like our model to be able to generalize to. For example, our train distribution might be a robot trained in a lab environment, and the test distribution may be actually deploying the robot in the real world, where we want it to be able to handle many different kinds of spatulas, essentially being equivariant to the kind of spatula that you give it. Or maybe the train distribution is ImageNet, and the test distribution is, again, some aspect of the real world that encounters various viewpoints and various different objects and different configurations. So when we're in a sort of situation, one natural reaction to this is, well, I have a lot of knowledge. I know how to generalize very broadly. For example, I know how to use lots of different spatulas. Can I build my knowledge into the algorithm to help it generalize to this test distribution? For example, we know things about physics. We know notions of objects. We have some notion of equivariances, such as 3D equivariance, like rotation and translation equivariance. We may have ideas for various architectures. However, I would argue a couple things. Well, I think that this is a very natural reaction. First, I think that while we humans are very good at generalizing, we don't actually know how we generalize and how we do it. There's really a whole field in neuroscience and cognitive science that's devoted to this topic of figuring out how humans are intelligent. And even if we did know how we accomplish what we do, we don't necessarily know how to program that into machine learning systems. And arguably that was kind of the approach taken by a lot of knowledge-based AI systems a while back. That said, even if you do think that we should build knowledge into our algorithms, the things that I'll be talking about today will still be useful. But in general, the goal of what we're going to be trying to do is doing a bit better than trying to build knowledge into the algorithm. And very concretely, the goal that I'd like to talk about in this presentation is, can we extract symmetries present in a set of data and transfer that knowledge of symmetries to new downstream tasks? Ultimately, with the goal of being able to learn that new task with less data, or learn that task in a way that allows you to generalize better. Okay, so this is our goal. Whenever you kind of lay out a problem, one natural thing to think about first is, well, are there any prior works that already solve this problem? And to my knowledge, the main classes of approaches that try to attempt to solve this problem is in the realm of trying to learn data augmentation strategies. And there are some works that have been mentioned at this workshop. Here are a couple other works that try to learn data augmentation strategies and apply those data augmentation strategies when learning new tasks or when learning with a new architecture. And these have been successful to some degree. One of the things that we're going to try to be doing differently in the work that I'll present here is, instead of trying to learn a data augmentation strategy and then apply that data augmentation strategy to a new task, we're going to try to build the symmetries into the model directly. And this means that we wouldn't have to actually augment the data for the new downstream task. We could simply learn on the data that we're given if the model encodes the symmetries effectively. Okay, so that's our goal and what we're going to try to do. And the way that we're going to try to do this is we're going to take a MetaLearning approach. So I'm going to give a brief primer on MetaLearning, just a few slides, to give a little bit of background behind the kinds of approaches that we'll be using. So I'll start with an example of how MetaLearning works. And in particular, let's look at few-shot image classification. So typically in few-shot image classification, you're given a small amount of training data, for example, one example of 5 different classes. And your goal is to be able to generate a classifier that can generalize to new examples among these 5 classes. So you have this little training data set and this test data set. Of course, generalizing, if you only have these 5 images and you're learning tabula rasa, generalizing from just 5 data points would be very difficult. And so the way that MetaLearning works is it tries to leverage data from other image classes in a way that directly prepares it for this few-shot learning task at test time. So say this is the task that we want to be able to perform at test time. The way that we're going to prepare our learner to be able to learn from a small amount of data is to essentially structure data from other image classes as if just in the same way as what we'll be seeing at test time. So we can kind of construct many different small training data sets and test sets, train a model such that after it's seen this training data set on the left, it can generalize to the data points on the right, and do this for a wide range of tasks. We'll do this across a wide range of training tasks, essentially learning how to learn each of these tasks, so that when given a new task at test time or meta testing time, we can generalize with a small amount of data. So essentially we're matching what train and test will look like, or what meta train and meta test will look like. Okay, and in this example, each of the tasks are image classification tasks, but they could also be other tasks like regression tasks, they could be reinforcement learning tasks, or other things. You can essentially replace these rows with other forms of machine learning problems. Okay, so that's kind of an example of the typical training setup for a MetaLearning algorithm. And the way that there's a couple different approaches for how to actually structure the algorithm for a MetaLearning approach. One of the simplest approach would be to simply parameterize a learner using a neural network. And the way that this works is you take your training data set with the corresponding labels, you pass this into a neural network, you also pass in the new test example, and train it to output the correct label for this example. And you do this for all of the tasks. You essentially train this network with supervised learning for all of the tasks in your meta training set, training it to be able to generalize from the data that you're providing it as input. So essentially you're training this function f that takes in training data and test input and is trained to be able to generalize from the data that's being passed in. So this is one approach. Another approach to this MetaLearning problem is, instead of just using this black box neural network, we might embed an optimization inside the neural network itself. So we might take an initial set of neural network weights, take the training data points, run some optimization procedure on this training data, for example, gradient descent. This produces a new neural network. You can then give the test example to this new neural network and train it to output the corresponding label, backpropagating all the way through the optimization process itself into any kind of learnable parameters of this optimization, whether it be the initial weights, the learning rate, and so forth. In many ways, you can sort of view this as the same form of MetaLearning that I showed on the previous slide, except you have this optimization process that's embedded inside the learner. One specific instantiation of this idea is the model-agnostic MetaLearning algorithm, which learns a set of initial weights that is particularly suitable for a few gradient steps of fine-tuning. And it works with kind of is allowed to be able to fine tune with very small data sets. Okay, so that's a very brief primer on MetaLearning. Now I'd like to get back to the main topic, which is how we might MetaLearn symmetries. And in particular, this is a project that was led by a PhD student in the lab, Alan Zhao, and an undergraduate, Tom Knowles. And the question that we wanted to look at is, can we recover equivariant and invariant structure via MetaLearning and then transfer that structure to new downstream tasks? Now, the first question you might ask is, well, do MetaLearning algorithms already do this to some degree? And so if we look at the mammal algorithm, for example, one thing we might note is that mammal can learn equivariant initial features if that's helpful for generalizing to the task. However, that equivariance may not be preserved in this gradient update. So this kind of resulting network may no longer actually share that equivariant strategy or that equivariant structure. So this is a bit of a problem if we actually want to specifically encode this sort of symmetry structure into the learning process itself. So what we're going to try to do instead is to essentially decompose the weights of a neural network into the equivariant structure or the symmetry structure and the corresponding parameters. And then if we can do this, then in this inner loop, in the gradient step, we can only update the parameters and retain any equivariant or invariant structure. Essentially embedding that into the architecture itself and allowing it to retain and preserve that structure throughout the learning process. And this should allow us to generalize to data points that are transformed according to the equivariance that it learns. Okay, so this is kind of at a high level of what we're going to try to do. So how might we actually do this? To think about solving this problem, we're first going to look at how equivariances are represented in neural networks. And we can first look at a very common and well-known example, which is convolutions. So if we look at a 1D convolution layer, it looks something like this, where you have an input X, a filter W that is slid across the input, and the output Y1, Y2, Y3 that corresponds to the different positions of the filter. Okay, so this is 1D convolution. How might you represent 1D convolution as a fully connected layer? So if you wanted to represent the same exact function, but with this kind of fully connected or affine layer, it would look like this, where you have this dense matrix where ABC is copied multiple times and the other parts of the matrix are 0. So this is kind of, this kind of gives us a little bit of insight about how equivariance is represented in the sense that it corresponds to a certain weight sharing pattern and also a certain weight sparsity pattern. Now, what we can do is, as I mentioned before, we want to try to kind of separate out the equivariant structure with the underlying parameters A, B, and C. So what we're going to try to do is we're going to try to reparameterize this weight matrix W into two parts. One part that represents the weight sharing or the symmetries, and another part that represents the underlying parameters. So the way that we'll do this is we'll have a vector that corresponds to the underlying filter parameters, and then we're going to have a matrix that represents the symmetries. And basically each row of this matrix will correspond to a different entry in our weight matrix. And this sharing matrix will essentially govern how weights in a fully connected layer are shared. So essentially we'll take the matrix vector product of the sharing matrix and the filter parameters. This will give us a vector, and this will correspond to a vector of weights. We can then reshape that into the weight matrix here. And kind of the key idea here is that the sharing matrix is going to capture symmetries, and the vector V will capture the underlying shared parameters. Okay, so that's kind of the first idea. We can run through one more example. So say we want to represent a permutation equivariance example rather than trying to represent translational equivariance. What this might look like is we might have, say we have a V vector that has two underlying parameters. We have a sharing matrix that looks like this. If we then take the matrix vector multiplication, we get a vector that looks like this. and we reshape this into a layer of weights here, and this gives us a weight matrix that is permutation equivariant, such that if you permuted the two inputs x, the output would also be permuted. Okay, so this may seem a bit hand-wavy, and so one kind of theoretical thing that we can say about this particular reparameterization of a weight matrix is that you can theoretically show that this particular reparameterization can directly represent decoupled equivariant sharing patterns and filter parameters for all group convolutions with finite groups. And this is important because this means that we can represent a wide range of different symmetries in this sharing matrix. This doesn't necessarily say that we're able to learn these symmetries, and we'll have some experimental results at the end that discusses this, but it importantly means that we can actually represent these. We can represent kind of a wide range of group equivariances. Okay, so that's the first idea, is we're going to reparameterize a weight matrix by this sharing matrix and the underlying parameters. And then the second idea is we're going to combine this with MetaLearning in order to learn the symmetry structure that exists in a set of data sets. And in particular, we're going to take the mammal algorithm, and in the inner loop of that optimization, we're only going to update the parameters v of each weight matrix, and we're going to keep the equivariant structure u fixed. So this will allow us to kind of encode and preserve symmetries within the network architecture. So in the convolution example, we would kind of preserve the fact that it's a convolution function and kind of change the underlying filters of that convolution function. And then in the outer loop, we're going to learn this equivariance u, and we're also going to learn the initial set of parameters v, similar to the way that mammal learns a set of initial weights as well. Cool. There's a question. I'll take this question maybe after I kind of finish describing the method. So this is kind of a visual depiction of the way that it works. So this first row is showing the inner loop. This box is indicating the weight matrix. U and V is the decomposition of that weight matrix. We take the inner loop loss, we run this gradient in, and we have it only update V and keep U fixed. V is updated, and then in the outer loop, we run the evaluation on X test to produce the corresponding prediction. Okay, and now one important assumption for this meta-learning procedure is that we're assuming that the symmetries that we want to capture are shared by all of the tasks in our meta-training set, and also shared by our test task. This is how we're going to be trying to transfer the symmetries that we learned from our set of meta-training tasks to our new held out task. Cool, and we'll use the acronym MSR, or Meta-Learning Symmetries by Reparameterization, to refer to this approach, not to be confused with Microsoft Research, of course. Okay, a few additional notes on this method. First, the symmetry matrix U, it is not necessarily binary or discrete. So in this example, it was a matrix of zeros and ones, but in other examples, in practice, we kind of initialize this somewhat randomly, and it can learn continuous values inside this matrix. This is useful because there are examples such as 45-degree rotation where we may want to kind of have kind of non-discrete values inside this sharing matrix with like a bilinear interpolation sort of thing. The second note here is, which might actually address the question, is that this sharing matrix U is quite large. It's going to be the size of the number of underlying parameters times the number of parameters in that layer. In some of our smaller experiments, we were able to represent the full matrix. In some of our larger scale experiments, we used a different kind of a way to approximate this matrix. So for example, we can use a Kronecker factorization of this matrix to represent a smaller number of parameters. You could also use something like low rank potentially, although we haven't done a thorough analysis of which approximations make the most sense. And then the last note is that W, which is kind of the weight matrix that we're reparameterizing, all the examples that I talked about before were with fully connected layers, but it could also correspond to weights for other kinds of layers that are not fully connected layers. So for example, W could also correspond to the weights of a convolution layer. And then what this would correspond to is essentially building in translation equivariance, which is what convolution gives you, and learning other symmetries on top of translation equivariance. And this kind of gets back to my point before, is that if you know some of the symmetries that exist in your data and want to learn other ones, then this gives you a means to do that. Okay, so now let's go to the question. The question is, won't the sharing matrix increase in size for permutation invariance for large numbers of permutations? Right, so as basically the size of your weight matrix grows, as the size of W grows, for example, your sharing matrix will have more rows. As the size of the number of underlying filters grows, you'll have more columns. And so yes, the sharing matrix may get quite large depending on what sorts of equivariances and invariances that you want to capture. Okay, and I think that the solution to that may be to use various approximations, such as low-rank factorizations or Kronecker factorizations, but I think that that needs a lot more investigation to fully understand. Okay, so let's go to some of the experiments that we ran. The first question that we asked is, can we recover convolutions from translationally equivariant data? To do this, we generated synthetic data, so we generated a number of 1D convolution functions. And we measured the mean squared error on held out test tasks. And what each of these rows are corresponding to is the mammal rows are corresponding to mammal with different kinds of architectures, either a fully connected architecture, a locally connected architecture, or a convolution architecture. The convolution architecture does very well because this perfectly exhibits the equivariance that exists in the data. And then MSR FC corresponds to MSR, where the layer weights W correspond to a fully connected network. And what we see is this is able to perform comparably to mammal with convolutions, which suggests that it's able to extract the translationally equivariant structure in the data. And further, we can actually visualize the weight matrix that we get as a result of running the MSR procedure. And we get a weight matrix that looks exactly like the fully connected representation of convolutions that I showed before, where you have kind of weights A, B, and C, and these are replicated across the matrix. Cool, so we're able to recover convolutions, or a 1D convolution from 1D translationally equivariant data. Now, the second question we asked is, can we recover something better than convolutions if our data doesn't have full translational equivariance? So we looked at data with partial translation symmetry, and in particular, we looked at low-rank locally connected layers with rank 2 and rank 5, and we found that we were able to learn something better than assuming that the data was rank 1 convolution, which is what mammal conv does. We also looked at data with translation, rotation, and reflection symmetry. And in this experiment, we applied MSR on top of a convolutional network. So we were building in the translation symmetry, but trying to learn rotation and reflection. And we were also able to find that we're able to do significantly better than mammal with a convolution architecture. Okay, cool. So these were just some experiments with synthetic data. We also looked at one experiment with augmented real data. And in particular, what we wanted to try to understand is if we could essentially build in data augmentations into the architecture of a neural network. And what this corresponded to is we took a set of meta-training tasks and a data augmenter. We took the train val split of the data for each task. We augmented only the validation set, only the kind of data points that are used after the gradient update inside the MetaLearner, and trained it such that after it saw the unaugmented data, it was able to generalize to the augmented data. So essentially, we wanted to try to bake in the data augmentation into the architecture or into the update rule, depending on how you look at things. And what we found here is that in general, when looking at augmented omniglot and augmented mini ImageNet, where the augmentations corresponded to a variety of things such as rotation and reflection and so forth, we are able to do significantly better than mammal, kind of as the approach that I described before, we also compared to a mammal with a larger architecture in order to control for the number of parameters between mammal and MSR. Further, we compared to almost no inner loop or ANL, which potentially has the ability to learn equivariant representations of the input and then learn a linear layer on top of that. But we also find that this doesn't perform as well as MSR, which is able to extract the equivariances. And then we also compared to prototypical networks, which is another meta-learning approach as well, and are able to find that we're perform it somewhat comparably or better in the different settings. Okay, so kind of one takeaway is that this approach for meta-learning symmetries provides a framework for understanding the interplay of features and structure in meta-learning, and potentially provides us as a route towards learning symmetries from data. Of course, I think that any work may open more questions than it answers. So I think that in the process of this work, we kind of ran into a number of really interesting open questions. So overall, we're interested in questions like, are there other approaches to represent and learn symmetries other than data augmentation approaches and other than MSR? Can learned symmetries improve generalization and robustness on downstream tasks? This isn't something that we explored very directly in our experiment so far. Also, things like convolutions also come not only with the translational equivariance, but also with very efficient GPU implementations. And if we're going to be extracting equivariances, are there other ways to extract some of the computational benefits of convolutions? And then some other questions that are more specific to MSR is, first, the sharing matrix that we learn may capture domain-specific information beyond the symmetries, and this may hurt transferability. So can we essentially figure out how we might regularize this sharing matrix that encourages it to only recover symmetries and not other domain-specific information? Second, how much data do we need to learn U, especially when U might be quite large? And are there more memory efficient or computationally efficient ways to represent this matrix? Great, so I'd like to thank my students, especially Alan and Tom, who led this work. If you're interested in learning more about meta-learning and multitask learning, I teach a course, CS 330, and all the lecture videos are available online, and I'd be happy to take some more questions.
Okay, great. Thank you very much for this exciting talk. And, there is a number of questions. So somebody who looks like anonymous. Why would one augment the validation set and not the training set, since this is the one where the transformation should finally be applied? And apparently this point was already there in this fast auto augment paper, which the attendee did not quite understand this point. I'm not sure.
Yeah, so part of our motivation behind this experiment is maybe kind of looking forward into future work where maybe during meta training we have the ability to augment our data, perhaps because we're training on simulated data, for example, and can rotate objects in simulation, but we can't do that on real. But maybe at test time it's harder to apply those augmentations. So in those sorts of settings, we want to be able to learn from data that isn't augmented at test time and be able to adapt to that while preserving these equivariances. And that was part of the motivation behind that experiment. If you augmented both the training set and the validation set, then the method would expect to see augmented data at test time.
Okay. So another question from Stefan: is it possible to decouple the idea of using a skeleton weight training matrix to learn equivariances from MetaLearning? I'm not sure. Do I understand this question? Decouple.
I'm not sure what they mean by skeleton weight.
Oh, maybe I'm not sure if this is the question, but I kind of a related question that I had was: is it or maybe this question? So you found a way to write down the kind of convolution in your example as a kind of product of these two, like the U matrix and the V, right? So if somebody comes up with another way of representing kind of a symmetric weight matrix, would it be possible to kind of, like, basically this is one component and the MetaLearning is another component, right? So somehow is it crucial that you represent the symmetry in this particular way, right?
Yeah, so I think that there could be other ways to represent the symmetry, certainly. And so this particular reparameterization is one idea that we introduced, but the second idea that we introduce is MetaLearning the symmetry matrix and keeping it fixed. If you had another way to represent the symmetry, then you could also apply the idea of MetaLearning to that symmetry matrix. The critical kind of aspect of that idea is that you only update the parameters in the inner loop and keep the symmetry fixed. And that sort of idea could apply to, this idea could be applied to other reparameterizations as well.
Yeah, because for instance, in some of these papers on spherical CNNs, people like expand in some sort of basis like the spherical harmonics, and maybe one can somehow learn the but I'm not sure if one can learn the spherical harmonics, but one can learn the coefficients of them possibly across tests. I'm not sure.
Yeah, absolutely.
Yeah. And the kind of final question, from Robin Walters: do you encourage orthogonality or sparsity in the columns of U through regularization?
Yeah, so in this work, in all of the experiments that I showed, we didn't actually place any regularization on U. I think that this would be something that would be quite interesting to explore in the future, kind of as I mentioned in the open questions, to try to encourage it to capture symmetry-specific information and not capture other information. But this is something that I think is left for future work, and I could definitely see that improving the results.
Okay, great. So in the meantime, there was yet another question posted. So from Juan Cerviño, what would happen if the symmetries in the data are located in one place of the image, but in the test set, they are located somewhere else? How would this work compared to normal convolution?
Yeah, so this method would not work in that setting if essentially the training task never had the symmetry exhibited there. You could imagine, well, yeah, if you're trying to kind of learn the same sort of equivariance that normal convolution is representing. Of course, you could build in convolution and then learn equivariances on top of that. It also might be possible that there are other ways to represent U that may encourage more forms of sharing across different parts of the image, or other ways to represent U that do allow you to handle that case.
Okay, great. Yeah, thank you very much for explaining that, and thank you for the very nice talk as well.